All right, we're at section 22.3, the law of refraction. And here is a table of indices of refraction. Uh, Now, what is the index of refraction? N is defined as the speed of light in vacuum uh, over the speed of light in a medium. So it would be C over V, where C is the 3.0 times 10 to the 8 meters per second, and V is some smaller velocity. No velocity is going to be greater than the speed of light. So we know that V will never exceed 3.0 times 10 to the 8 meters per second. It'll be like 2.85 or 2.93, something like that. It'll be something less than 3 times 10 to the 8 meters per second. I do want to point out there's an error. There's an error in the physical textbook. There's an error in the PowerPoint, and there's even a error in your ebook. This should be this table 22, indices of refraction for various substances measured with light of vacuum wavelength, lambda 0 equal 589 nanometers, nm, nanometers. They have mn. It's printed like that in the physical book, the ebook, and the manufacturer slides. I tried to correct it, but I couldn't. I tried to type over it, but you would still see the image below it. What is 589 nanometers? I can show you. I've got a little, where is it? Where's my Mathematica? Oh, there it is. That's 589 nanometers. I have a little device here that you can play with the wavelength. This 400 nanometers is very, very dark purple, all the way to 700 nanometers. It's a real deep, almost blood red, dried blood red. So 589, let's see if I can't quite get to it. I'll just type it in. 589 is this orange, kind of the orange color. And you'll see that later when we talk about dispersion. But anyway, that's what they use in this table, indices of refraction for various substances measured with light of vacuum wavelength, lambda 0 equal 589 nanometers. Okay, so let's look at some of these indices of refraction. You can see the largest one here is a diamond, 2.419. Now it's unitless, because if you have 3.8, 3.0 times 10 to the 8 meters per second over some other velocity meters per second, well, the meters per second cancel, and you're just left with a unitless index. So diamond is 2.419. Let's see what's another high one. Zircon, 2.923. Of this batch, the lowest is, I'm talking about the solids. Ice, ice is 1.309. Let's look at the liquids. Water is about 1.33. The highest one looks like carbon disulfide, 1.628. And then if you look at the gases, well, I doubt if you'd be able to really see that. Air is 1.000293. Carbon dioxide 1.00045. Those are essentially 1.0, same as in vacuum. Anyway, let's continue on. Now, as a wave moves from medium 1 to medium 2, its wavelength changes, but its frequency remains constant. As it moves past observer A, it's going to have a particular frequency. Well, as it moves past observer B, it's going to have the same frequency, but the wavelength will be shorter because it's traveling at a slower velocity. Let's look at some of these equations. Velocity is equal to the frequency times lambda, and in this case, the frequency is the same. F1 equals F2 equals F. So the velocity of 1 equals f lambda 1, and the velocity of 2 equals f lambda 2. Well, if we divide one by the other, you get lambda 1 over lambda 2 equals v1 over v2. Well, since v equals speed of light over n, you substitute c over n1 for v1 and c over n2 for v2. Those cancel, and you end up lambda 1 over lambda 2 equals n2 over n1. And if you cross multiply, you get lambda 1 n1 equals lambda 2 n2. So n is for if you take it in vacuum, n is just equal to 1. So for the index of refraction, n is equal to the wavelength in vacuum divided by the wavelength in the medium. Okay, and here it's just a representation. You can see lambda 1 is from trough to trough is this length, but in N2, it's shorter. Lambda 2, this is when the index is greater than N1. Lambda 2 is less than lambda 1. And at the very bottom, you get what is called Snell's law. N1 sine theta 1 equals N2 sine theta 2. And in most cases, we use the N1 being air, which is 1.000, whatever it was, 1.0 for our purposes. So the theta 1, if you recall the images, theta 1 is the incident angle, and theta 2 is the angle between the refracted ray and the normal. That's how you get theta 1 is the incident ray to the normal, and theta 2 is the refracted ray to the normal. And it'll always be less, theta 2 will always be less than theta 1. Okay, and that's it for the law of refraction. We'll go on to dispersion next time.